Welcome everyone to the September A3D3 seminar. It's my very great pleasure to introduce today's speaker, who is Andreas Søgaard. He's a Maria Curie Fellow at the Niels Bohr Institute at the University of Copenhagen. He received his PhD in experimental particle physics from the University of Edinburgh, working on the ATLAS experiment at CERN. After graduating, he was a postdoctoral fellow at the University of Edinburgh before spending a number of years in the private sector as a chief AI officer for a Danish data science consultancy, and has come back to academia to work on the IceCube experiment now. And the title of Andreas's talk is Machine Learning in IceCube. So Andreas, please take it away.
Thanks. I'll just be sharing my screen here. Should be seeing it now. Thanks so much for having me. Thanks, Matthew, for the kind introduction. And I actually had the pleasure of working with Shishi back in my previous life on Atlas. So it's good to be in good company. So I'm going to be talking on the very sort of expansive topic of machine learning in IceCube. So I'm not quite sure how many people in the audience are sort of native to particle physics and IceCube. I took the liberty of starting pretty much from scratch, and then hopefully we can make our way through that quite quickly and get to the interesting bits quite soon. So I'm going to be giving a very brief intro to IceCube, and then I'm going to be giving an overview of some of the machine learning applications that are currently being used and being sort of explored in IceCube. And then I'm going to finish on some considerations about how we work with machine learning in particle physics experiment more generally. But first off, just a quick word on neutrino physics and IceCube. So starting all the way at the beginning here on the left, you see the standard model of elementary particles, where you have the force-carrying particles like the photon and the Z boson on the right, and then you have the matter particles, the fermions, on the left, or the quarks and the leptons. And here I've highlighted the neutrinos because they are a really interesting group of particles coming in three flavors: electron, muon, and tau neutrino, cousins to the electron, muon, and tau. And they're really interesting because they're some of the most elusive particles in the standard model, which means that some of the least well understood particles as well, which is why we're interested in understanding them better. And they have a number of peculiar features to them that make them really interesting. One of them being that we know that they're massive. They have masses, even though the standard model tells us that they shouldn't. And this incompatibility is already a sign of physics beyond the standard model that we don't understand. So that's really intriguing. And the fact that they're massive gives rise to another interesting phenomenon called oscillations, neutrino oscillations. And that's because these flavor eigenstates, electron, muon, and tau, they don't have definite masses, which means that they're different from the mass eigenstates of the neutrinos. And what that means is that if you have a neutrino created in an interaction with a particular flavor, like electron neutrino, as shown on the right here, as it travels, because the mass eigenstates that determine the oscillation frequency when it propagates are different from the flavor eigenstates, it means that the neutrino actually changes type as it travels. It starts out as one flavor, electron neutrino, and it can end up in a different flavor some distance away as a muon neutrino. So that's really interesting. And the parameters that govern oscillations are some of the core parameters in the standard model, and are ones we want to measure. The problem with that, and the reason neutrinos are so elusive, is that they only interact through the weak interaction instead of the electromagnetic or the strong interaction. And as the name implies, that means that they interact with other particles only very rarely and very weakly. That means that they're very hard to measure, which is why we don't understand them that well. So when we have this very small probability of interaction with other matter, you need a very big volume of matter in order to have any sort of sizable probability of actually seeing them interact. And that's where the IceCube detector comes into play. So you see here on the left, and it's called the IceCube Neutrino Observatory. It's stationed at the geographical South Pole, so just right below the ice there. And as the name sort of cutely implies, it's 1 cubic kilometer of instrumented clear ice on the South Pole. And the reason that's quite smart, that we use sort of the ice as a passive medium and we get it for free, is that if you have a neutrino traveling to Earth from somewhere, and it moves into the ice and it interacts, the neutrino itself is invisible, but its decay products are not. So they actually interact and they produce a light that we can measure. And the decay products also produce what's called Cherenkov radiation, which is a very pale blue light. And because the ice is clear, that light can travel through the ice. And then what you can see here is a lot of strings that's been bored down into the ice with a number of detection modules on it. And when the light travels through the ice, it can be detected on these detection modules here. And that's what you see on the right here. These are called digital optical modules, and they contain photomultiplier tubes, which are basically just a single pixel camera pointing downwards. And nominally, IceCube has 5,160 of those sort of dispersed in this hexagonal grid of strings in the ice. That's what's called an optical neutrino telescope. So this is a very cool experiment. I've always found it a bit bonkers just to use the natural environment for your physics experiments, but it's quite elegant. But this is just a nominal configuration. IceCube is in constant development. So right now, the IceCube that exists today is shown here in the little hexagonal grid in the middle. And it's made up of a main array of 86 of these strings of PMTs, DOMs, digital optical modules, as well as the IceCube deep core, which are the green strings here in the middle, which is an array of more closely spaced strings with more closely spaced DOMs that enables IceCube to really probe the low energy range of the neutrino spectrum. But then there are 2 additional extensions planned for IceCube. One shown here on the left, which is the IceCube upgrade, which is a set of even more closely spaced strings within deep core for even better instrumentation for low energy neutrinos and better measurement of the oscillation parameters that I just talked about. And then you have the IceCube Gen 2, which is this 8-fold increase in instrumented volume that's planned for an 8 gigaton experiment that's going to target even higher energy neutrinos with a bigger fiducial volume for greater pointing precision and multi-messenger astronomy. So IceCube is clearly a very complex thing, even if it's quite elegant, and the different subdetectors are capable of probing many different aspects of the neutrino sector. Of course, I haven't quite answered the question yet of where those neutrinos actually come from in the first place. So just make this little cartoon here, where we have the Earth turned upside down, right side up if you're from Australia, I guess, with an IceCube indicated all the way right there at the top on the South Pole, and then a cartoony atmosphere drawn around there. And the dominant process that produces particles that we actually observe in IceCube is actually not neutrinos, it's actually muons. And these are produced when the cosmic rays impinge on the atmosphere, decay into muons, which can travel quite far. And then they can travel down through the atmosphere, down through the ice, and into the IceCube experiment. Which means that they manifest as something visible coming in from outside and maybe going through the detector or stopping in the detector. So this is our main physics background. So muons are cool, but for our purposes, it's not really what we're interested in. So we want to sort of, this is the haystack in which we want to search for neutrinos, so to speak. And we actually measure these muons in IceCube at a very high rate. It's about 1 kilohertz. So 1,000 of these per second is being detected in IceCube, which is quite a lot. The first source of actual neutrinos are what's called atmospheric neutrinos, and they're produced in a very similar way through cosmic ray interactions that produce neutrinos. But the key here is that while muons can only travel through the atmosphere and maybe a little bit into the ice, neutrinos, as I said, interact very weakly, which means that neutrinos produced on the other end of the world can actually travel pretty unaffected through the Earth and get to the IceCube on the other end. Which means that these manifest in a very different way from the muons in that they're predominantly upgoing. They come up through the mantle of the Earth and into IceCube that way rather than being downgoing. And they manifest as invisible particles that enter IceCube, invisible, interact with the ice, produces particles that are actually visible and whose radiation we can detect. And the reason that atmospheric neutrinos are so interesting for oscillation measurements is that neutrinos produced at sort of every latitude around the Earth can travel through the Earth and get to IceCube, which leads to a very natural spread in different baseline distances that these neutrinos will have traveled, because they're all produced as muon neutrinos, and then they travel different distances, which means that we can measure like what flavor composition we get as a function of the latitude, which is really interesting for oscillation purposes. I should say that these are much, much more rare than the muons. So they are factor 10 to the 6 less frequent, like now we're in the millihertz range. And lastly, we have what's called astrophysical neutrinos, which are neutrinos that are not produced in the atmosphere near Earth, but produced somewhere else in the cosmos in high energy astrophysical processes like the sun, supernovae, blazars, and so on. And they manifest in very much this similar way as the atmospheric neutrinos. We're going to end up looking for them in an upgoing direction, and they're going to manifest as something invisible entering IceCube and then interacting with the ice. And they're characterized by their very high energies. So this is in the PeV or 1000 TeV range, and potentially their coincidence with other astrophysical measurements in other sort of modalities like optical telescopes or gravitational waves even. And these happen at a rate of around once a month. So these are very rare processes that we actually detect them. So these are the processes that generate the particles that we're actually seeing in IceCube. But then what does it look like when they actually interact with IceCube? I've included this little film that I hope you should see here. So it's a brief animation of a simulated neutrino interaction in IceCube, where you see a muon neutrino entering from the top and not really producing any light. And then it interacts with the ice to produce a muon. And the muon is moving at relativistic speeds, meaning that it emits the Cherenkov light. And then the light that's being detected shows up as these colored blobs on the strings. And the color of the blob indicates the arrival time, and the size of the blob indicates the number of photons that's actually collected by the individual optical modules. So this is sort of what our data looks like in IceCube. We have the timing, the position, maybe the direction, and then the amount of charge that's collected for each pulse or each sort of detected photon in the event. And these events last on the order of a few hundreds of nanoseconds. So the goal of what's called Reconstruction in IceCube is to take this data that's collected by the DOMs for all of these events that happen at a kilohertz rate, and then try to say what happened, what particle gave rise to this, what were its properties, and so on. And one of the main tasks we do in Reconstruction is trying to identify what type of interaction took place to produce a specific event. And here there are two dominant categories as sort of the regular energies that we think of that we use. So we have what's called track-like events. that you see on the left, and then we have cascade-like events that you see on the right. And track-like events are produced by muons, either produced in cosmic ray interactions starting outside of the detector, or produced in so-called charge current interactions with a muon neutrino producing a muon in the ice. But they're all characterized by a high energy muon that travels a long distance in the ice, emitting Cherenkov radiation as it goes along, giving rise to this sort of elongated shape on the left. The other topology that we encounter are what's called cascade-like events. And these are the ones that are not elongated, that are pretty symmetrical and spherical in the radiation pattern. So these can come about from charge current interactions involving electron neutrinos or tau neutrinos, which don't travel these long distances and actually just decay and lose all of their radiation in at a very short distance. Some tau neutrinos can actually decay into muon neutrinos, and muons, that's different kettle of fish. And then in neutral current interactions, where you have the neutrino exchanging a Z boson with the ice, and then escaping again as an invisible neutrino, and then all of the radiation comes from the hadronic shower. Based on these two topologies, the timing and the amount of light, then our test becomes to reconstruct the underlying process, like what gave rise to this event and what energy did the particle have, where did it come from in the sky. But of course, this is a little bit of a hard problem because our data is not really trivial, right? We have very high rates, kilohertz rates, and IceCube has been taking data for upwards of 10 years. There's a vast data set. And the charge deposits in IceCube are often quite sparse. They don't fill out the entire detector. You have a lot of empty space in your event, so to speak. With a very sort of non-trivial geometry, hexagonal. It's not a nice square grid that we know of from other applications. Then we have these nested subdetectors that are not geometrically heterogeneous, which means that some of them are more tightly spaced than others. And when we get the upgrade and the Gen 2, that challenge, it really exacerbates. And one of the benefits we have is that we actually have the same detection method, photomultiplier tubes, across all of our subdetectors, which is actually a boon for us in some sense. So taking all of this, these vast amounts of complex data and then trying to extract some key parameters from it is a little bit hard. So how can we then analyze this data to make predictions about the underlying process? And historically, this has been done in sort of a very precise, physically motivated analytical way. So the current state of the art in terms of these classical approaches to reconstruction is called retro, or reverse table reconstruction, with a little reference there. So what this does is that for each event, it models the underlying process as a neutrino that has some energy that goes into a muon that travels some distance here in the blue cones, and some energy that's deposited in a cascade shape. Very detailed, very precise, and then the reconstruction of these theta parameters that characterize the event is an explicit likelihood for each DOM for finding pulses at specific times given an 8-dimensional parameter set comprising the location of interaction vertex, the pointing direction, and the energy depositions in the track and cascade topologies, so to speak. And for every event, this optimization, this minimization of the likelihood on the slide here is done. And you can see sort of a slice of a likelihood contour here on the right in 2D of these 8 dimensions in total. So this is clearly very involved and very precise, but it also means that the reconstruction times, the inference speed, is quite slow. It takes about 40 seconds to reconstruct every event using retro in this way, because it's a very detailed procedure. And that means that basically we're computationally limited to using much simpler and less precise reconstruction methods early in the reconstruction chain at these kilohertz rates, in order to remove the dominant backgrounds quickly, or in a quick and dirty way, and then only use retro and these very detailed reconstruction techniques at the very end, once we've removed the majority of events, when it actually becomes feasible in terms of rates to use these very time-consuming methods. That's of course a very unfortunate trade-off to have to do between reconstruction performance and reconstruction speed, and ultimately for physicists like us, it means that we know that we're essentially limiting our physics results because we're not using the highest precision reconstruction at every step of the way, and that's really unfortunate. So thinking goes, it would be really nice if there were a way to have fast, high fidelity reconstruction that we could use like almost at trigger level, almost at these kilohertz rates, and not sort of limit ourselves to simpler heuristics, which is of course where machine learning comes into play, because it promises fast, performant reconstruction by splitting the training. That's very cumbersome and time-consuming, but you only do it once, from the inference, which doesn't involve any optimization and iteration in the way that retro does, which is a single forward pass. So of course, a lot of work has already been done on machine learning in IceCube from ways back, from boosted decision trees over random forest to deep neural networks and convolutional neural networks and so on. And that's just the 50 odd public results, and there's a lot of stuff going on that's not yet public. And the progression and maturation of in IceCube has followed a very similar pattern to that in other large-scale physics experiments like those at CERN, where we've gone from simple analysis level models that's trained on high-level engineered sort of expert features. That could be BDTs, random forest, and shallow neural networks. Just like into deep learning, but just like simple stacked MLPs that still only act on engineered features, to these more complex multi-purpose models that work on the raw data, the low-level features, and that could be recurrent neural networks or convolutional neural networks that has a geometric structure that I'll get into in a little bit. And then you can also have deep learning models with a dynamic geometric structure that's not locked in a certain sort of paradigm, but we'll get to that. So these simpler machine learning paradigms, they only act in the engineered features, while the deep learning models with geometric structure can act on sort of the raw low-level data, the pulse data from IceCube in this case. And this is feasible. Processing these massive amounts of data is feasible due to the advent of specialized hardware, such as GPUs and TPUs, that reduce training time to something like at least an order of magnitude faster than CPUs. And then this separation of training and inference. We can do the time-consuming training once, and then just do a single forward pass for every event. And the modeling complexity of these deep learning models means that we're able to do extremely performant reconstruction on specific tasks. And the fact that we're not doing any optimization means that we can achieve a factor 1,000 speed up, like order of magnitude, in terms of these classical alternatives, which means that we can move the deployment of these models much earlier in the reconstruction chain and reap the benefits of that, which is going to have some large downstream effects on our physics results, which is really appealing. So I'm just going to I'm going to focus on the neural networks that have been used in IceCube and that are being used in IceCube, because they encompass sort of they're a very flexible paradigm for doing machine learning. And within neural networks, like what different architectures could we employ in IceCube to perform this reconstruction? So first we could do just stacked sort of MLPs, multilayer perceptrons, what I just call deep neural networks with no inherent geometric structure. Again, that's good for high-level event features like those you have derived in an analysis at a very late stage. But in order to ingest raw data, you could also use recurrent neural networks that are good for having sequential data in a sort of a time-ordered series. And then, you also have convolutional neural networks that sort of have a geometric structure with orthogonal data that we expect to have some translational invariance that's encoded in the convolutional kernels. That's good for images and so on. And the latter here, convolutional neural networks, have actually been used in IceCube with quite impressive results to show for it. This was used for high energy cascade reconstruction, I mentioned earlier, where on the left here, you see a comparison in pointing resolution for a CNN-based model compared to a standard likelihood-based model. And we see that at high energies, it yields a 50% improvement in resolution, while at the same time on the right, it reduces the runtime per event by 2 to 3 orders of magnitude, even on a CPU. So we don't only get improved resolution, we get it 1,000 times faster than these otherwise like quite detailed high fidelity reconstruction algorithms like Retro. So that's really impressive. And it shows that machine learning as a reconstruction method in IceCube has quite big potential. So this was done with a convolutional neural network, and it works quite well. But there are some conceptual challenges to CNNs and IceCube that are sort of worth considering. And one of them is that we have nested detectors, and CNNs aren't built for that. They're built for images, which means that if you want to process the main array and deep core, you need to split them up and treat them separately. That's what's shown here at the bottom. This is from the same paper as the results I just showed you on the last slide. So just to treat the main array and deep core separately, which means that inevitably you're sort of weakening the local correlations between the radiation patterns in these two detectors that actually, ought to be quite correlated. And the fact that you also need to take these hexagonal arrays and sort of shift them into these square grids as shown here on the bottom in order to fit them into the CNN paradigm and have them use these square kernels. And sort of any modification to the geometry of your data inevitably has to sort of mean that you lose some details in the process. And the fact that CNNs work on sort of pixel level means that you have to process also all of the empty pixels, all the empty DOMs that weren't hit in a specific event. And for DOMs that are hit with multiple pulses, as they are at high energies, you need to summarize them. You can't sort of leverage the fact that you have a series of pulses on each DOM. You need to summarize them into some averages and counts and so on, which means that you're losing a lot of the granular information that IceCube's data actually has to offer, which is a shame. And then in this paper, they also deploy some hexagonal kernels in order to get around these geometrical limitations. But the more specialized your approach becomes, the less likely it is that other experiments that have the same problems can use those sort of advancements, which is again a shame. So these three paradigms, DNN, RNN, CNN that I just mentioned, they don't really fit the geometric properties of IceCube's data, which then begs the question whether there's a more natural paradigm in which we can work with our reconstruction. And I think one of the really important point here is that we have all these different architectures, but you can sort of think of them as special cases of a more general type of architecture, which are called graph neural networks or GNNs. And in this case, you represent all of your data, which in our case would be the properties of the collected pulses in the eyes, as nodes on some graph, some abstract graph. And the nodes are then connected by edges, which label here Aij in this little figure here. And the neat thing about graph neural networks is that they don't impose a specific geometrical structure. You can encode any structure you want through the connectivity or the adjacency of the different nodes here. So in our cases, the pulses would be the nodes, and the edges would be the propagation, the message passing, the exchange of information between the nodes as we go deeper into a deep graph neural network, so to speak. We've come to think of GNNs as a very natural choice for IceCube, because the fact that there's these sparse charge deposits in IceCube, it's not a problem for graph neural networks, because for a CNN, you need to process the entire event, which is a little bit wasteful if 90% of it is just empty space. But in a GNN, you can just construct a graph that only encompasses the PMTs that were hit in each event. And the fact that you have hexagonal geometry doesn't really matter, because you can you're not limited to an orthogonal geometry. You can, there are no parameters in the structure. You can encode any geometric properties you want through the graph connectivity. And the fact that there are nested subdetectors like Deep Core, IceCube Upgrade, Gen 2, again, it's not really a problem, because all the nodes can be connected with any other node. There's no need to treat them separately, which means that we can have exchange of information between all nodes, between all DOMs, regardless of what subdetector they just happen to be a part of. Another plus is that because each pulse can represent a node, there's only to summarize the pulses to the DOM level as there is for the CNN. We don't need specialized kernels, which means that we can more easily generalize our techniques to other experiments like IceCube. And we can actually encode physics information and material properties and so on into the structure of our convolution, into the structure of our networks. So the connectivity between different nodes could be based on the Euclidean distance, or some Minkowski distance, or it could encode the scattering or absorption properties of the ice between two distant DOMs, which is really interesting, that we can actually bake some physics into the machine learning. As a physicist, that's really appealing. And as with all deep learning, we have the benefit of just blazingly fast inference compared to likelihood-based reconstruction. So those of you who aren't familiar with GNNs, I'm just going to go through what those look like under the hood, just to give you a feeling of the anatomy of a GNN. And our input would be the pulses, just a collection of nodes in some abstract space. Then we need to decide on some graph connectivity. It could be based on connecting all DOMs within a certain distance in meters, or weighing the adjacency based on 1 over the distance or something like that. And this is where we can actually bake in the physics of our experiment. Then we can do convolutions or message passing or information transfer between the individual nodes in our graph. We can do sort of MLP-based updates on the features on the individual nodes, and we can stack that, make it a deep GNN. And then we could use this to do node level predictions, which could be predicting whether an individual pulse came from electronic noise or from some physics process. So that could be one outcome of this sort of deep GNN. But we could also do some local pooling, sort of coarsen the graph, aggregate some of the pulses into clusters, and then do the same thing, do some message passing, do some updates, stack it into a deep model. We don't have to do that, the local pooling. We could just go straight to the global pooling, which means that we sort of aggregate across all of the different nodes, the features in some learned latent space, and then use this global event level feature vector to do event level predictions, like predicting what was the energy of the particle that gave rise to this event. So this is just a quick schematic to show you how you could build up and sort of parameterize a graph neural network. I'm sort of evangelizing GNNs here, but you can sort of fairly ask, are graphs always the right solution then? And since we have Shishi here, I can take a quick detour around CERN to sort of reflect on, what do other experiments, what are they doing in terms of machine learning? And the general purpose experiments at CERN, like ATLAS and CMS, they actually have calorimeters that are mostly pixelated. You can see the CMS eCal crystals on the top right there. And these are pixels. You have a few depth layers of those that correspond to color channels. It actually resembles the ideal CNN use case quite closely. So you could use CNNs on data from these calorimeters to do jet tracking or whatever. And it seems like a very reasonable and effective paradigm, and you see a factor of 2 improvement in background rejection versus sort of simpler analytical alternatives, which is good. You could always also use it for B-tagging, where, as it says here, RNN-based B-tagging algorithms can exploit the spatial and kinematic correlations between tracks when they're initiated from the same B hadron. Which sort of simpler methods don't really allow for because you have a variable number of tracks. And the notion of the impact parameter, so how far away from the primary interaction vertex the track points, gives you a very natural track ordering for the task. So here, RNNs could be a very reasonable and effective paradigm. And indeed, we see sort of a factor of 2.5 increase in background rejection versus comparable analytical algorithms. So this would suggest that maybe there are other experiments, other sort of data geometries for which CNNs and RNNs are actually a really good match. But still, these experiments have also employed GNNs. And even though these sort of examples should be really good use cases for CNNs and RNNs, we still see large performance gains by using GNNs, like a 40% increase in background rejection by CMS using GNNs over a 2-dimensional CNN, or a factor 2 to 3 increase in background rejection for B-tagging in ATLAS by using a single GNN over sort of a very involved combination of RNNs and deep neural networks and so on, and expert variables. And the same conclusion is reached in tracking, secondary vertex finding, pilot mitigation, and elsewhere, where we just generally see a significant performance improvement by using GNNs compared to otherwise well-motivated approaches. And I think this goes back to the point I was making earlier, that GNNs can be considered as sort of a more fundamental paradigm that generalizes the other ones and encompasses them. Meaning that it does as well as these other paradigms do, and maybe better. And I think that's what we're seeing here. So we can then sort of return to IceCube, because for IceCube, it does a priori seem like GNNs are a uniquely suited paradigm for our data and our problems, perhaps unlike what we just saw. So it's not a surprise that GNNs in IceCube have been sort of explored at least as far back as 2018, and also been explored by other experiments like IceCube, like KM3Net. But what I'm going to focus on today in terms of machine learning in IceCube are some hot off the press results from 5 days ago that are now on the archive. A new paper out of ATLAS called Graph Neural Networks for Low Energy Event Classification and Reconstruction in IceCube. So this is a Monte Carlo based sort of POC paper from IceCube on the use of GNNs for a variety of physics tasks that target the low energy regime here from 1 GeV to 1 TeV, that have a large potential to improve oscillation parameter sensitivity. And the event selection that was used in this paper actually sort of leverages an existing 7-step event selection that was designed for oscillation analyses with the goal of reducing the 3 kilohertz trigger rate to around a 1 millihertz rate in order to make it feasible to run some alternatives like Retro, which is the current state of the art in IceCube. So this has the implication that any performance gains that we will see from GNNs at this 7th level of an event selection, based on simpler methods out of necessity, actually are probably lower bounds on the impact that GNNs can have on physics analyses, as we could actually leverage them much earlier in the reconstruction chain. So this paper is based on a model that was titled DINEDGE, which, you know, the wiring is shown here on the right. It's a little bit hard to pass, but basically it takes all of the pulses in an IceCube event, connects the 8 nearest pulses to form the graph. For the first convolution, that's done in the classical XYZ space, and then for the 4 subsequent convolutional layers, the graph is rewired, reconnected to the 8 nearest pulses in some learned latent space, thin edge for dynamical edges. And then we have a single layer MLP-based edge convolution at each of these layers. We have skip connections, meaning that we also include sort of the first layer and the second layer and the third layer, stack them at the end. We do 4 global poolings and add a few high-level features. And then we do a single MLP layer readout to get event-level predictions. And all of the models we're going to see are single task models that train specifically for a certain task. So I'm quickly going to go through some of the performance studies that were done in this paper. The first one being neutrino versus muon classification, and that's in order to get a neutrino sample with a high purity. Then we do track versus cascade classification, neutrino energy reconstruction, and neutrino scene reconstruction, because these are the 3 dimensions in which oscillation analyses are typically binned. Then we're going to show a result on how this impacts oscillation contours are actually physics sensitivity, and then end on a note about how robust this is to systematic uncertainties. And the first was neutrino versus muon classification, because, as I mentioned, atmospheric muons are the biggest physics background, and we want to identify muons among this very big haystack in order to get a pure signal. So this is bug standard binary classification at the event level. And we see on the right here that at the same background rejection rate, we can actually improve our neutrino selection efficiency by 18% compared to the currently in use BDT that was trained sort of at the analysis level to do this task. Or we keep the same signal efficiency and increase the background rejection by a whopping factor of 8, which is quite impressive. Next, we get this track cascade classification. Because IceCube is not, ideally we would want to do a flavor-wise categorization, but we can't do that. We can only use these sort of track and cascade like events as proxies. And again, it's a binary classification task, track versus cascade like events, in order to get a handle on stuff like muon neutrino disappearance. And here we see a 6% improvement in rock area under the curve compared to the state-of-the-art BDT, which doesn't sound like a lot. That's of course because AUCs are a little bit hard to gauge, but in practice it means that the particle ID bins, the track versus cascade bins, become much cleaner, which means that the binning that's used in an oscillation analysis become much cleaner. Then for the neutrino energy reconstruction, again, because these analyses are binned in energy, a better energy resolution means sharper oscillation measurements, basically. So here we do 1D regression of the true energy using a log-Koch loss. And here we can actually compare to Retro, which does energy regression. So on the right here, you see the energy resolution for DINEDGE and for Retro as a function of the energy, high energies to the right. And of course, we want a low resolution, a narrow distribution of errors around the true value. And we see that in the range that we're interested in, so below 100 GeV or so, we see an average improvement in resolution of around 20% compared to Retro. And keep in mind that the main benefit that we were looking for was just to get a fast reconstruction because retro takes 40 seconds per event. But we also get a 20% increase in resolution on top of that. And keep in mind that retro is a very sophisticated algorithm. So this is quite impressive. And then we can do the same thing with the neutrino zenith direction, or like the latitude from which it comes, because this is basically the distance that the neutrino travels. And again, a better resolution leads to better oscillation results. Again, see retro versus thin-edge on the right, lower is better on the top plot. And again, we see that in the range that we're interested in, we see around a 20% improvement in zenith resolution across the board. And taking the past three together and sort of doing a simple toy analysis, ignoring systematic uncertainties and all those nasty bits, we can compare what the oscillation parameter contours would look like had GNN been used at this 7th level of evaluation versus what's currently being done. And that's shown here on the right. So smaller contour, more precise. And what we see is that the improvement that we see correspond to an additional 2.5 detector years, or 20% in terms of the area of this curve here. So that's a pretty big impact on the physics results, like 2 years of data taking plus by switching reconstruction algorithm. And again, this is the GNN deployed at the 7th level of event selection. If this had been tuned to work all the way from the kilohertz rate, like our gut feeling tells us that this would be even better. So this is quite encouraging. But then with these complex deep learning models, there's always this healthy fear that they're acting on the raw detector data. They might overfit patterns in the training data, not extrapolate well to unseen data, which would be data under different systematic variations. But then we compared like how the resolution and how the biases change for each of these different performance tasks for thin-edge and for retro under different shifts in systematic uncertainties. So on the right, you see each column here has different systematic variation, and then the impact on performance is shown by the bars. And basically what we see is that thin-edge has almost identical behavior to retro, which is entirely sort of physics-based, not this black box that deep learning models typically are, which suggests that the GNNs are not any more susceptible to these variations, and they're not, they don't seem to have a greater dependence. So this is again encouraging for physics use. So just to recap, GNNs provide a significant improvement in performance over alternative approaches like likelihood-based approaches or simpler machine learning approaches. And we can see that it actually can increase the sensitivity of oscillation analyses. And they provide speed-ups over likelihood-based reconstruction by orders of magnitude, which means that we can deploy these high-resolution reconstructions at near real time, at least very, very early in the reconstruction chain. And the fact that GNNs are so flexible, it means that it's seamless to extend to other sub-detectors, detectors, different DOM configurations using the same set of building blocks. So we can really take any extension of IceCube that they throw at us. And right now we've just done per event classification and regression, and we could do per node, like per pulse classification and regression. But of course, there's a lot of stuff that we could do beyond that. Anomaly detection, explainability, what have you. So this is just scratching the surface. But that brings us to the last thing I want to touch on, and hopefully be pretty brief about, which is we see that these GNNs are powerful, and if they make it to physics analysis, they're really impactful. Which then, to me at least, invites a discussion about how we actually work with machine learning in physics in order to actually make sure that they have the impact that we see that they can have. So I'm going to put a little spicy take here, that in experimental particle physics, machine learning only has real value when it's used on experimental data, which means for physics analysis, for calibration, and so on. But what I mean by that is that it's great to do one-off studies, proofs of concept, and so on, pheno papers. But it's only when we get machine learning models that are reliable, validated, reproducible, and actually use them in real physics analyses that we reap these benefits of ML for our science programs. Which means that how we work with machine learning, how we build machine learning systems, and how we deploy them in physics reconstruction becomes really crucial for this notion of success. So what are the challenges to this then? Why isn't it straightforward? And the challenge with machine learning is that it's typically not developed by experienced machine learning practitioners, meaning that often best practices, be that software engineering or machine learning, are not adhered to. That could be like clean code, structure, documentation, unit tests, continuous integration, continuous deployment, that sort of thing. Using the right machine learning paradigm, reproducibility, experiment tracking, uncertainty estimation. Maybe that's not really adhered to. We can lead to situations where we have brittle, sort of suboptimal, opaque ML solutions, and that will be a shame, right, for the physics. And often the machine learning that I've seen in physics has been developed from scratch in a very siloed fashion, where an individual or a group go off and do their own thing, rather than leveraging pre-existing work and tools. And the solutions are not developed with a holistic view of the different use cases, which often leads to this approach, because we're starting sort of from the bottom up. So in many machine learning efforts that I've seen in IceCube and Atlas, there's been like only limited coordination between different machine learning projects, very little reuse of code and tools, and each developing their own separate framework essentially, which means that a lot of time is being spent on quote unquote like reinventing the wheel for each different physics use case that we want to tackle. And the result is that machine learning work has a very short shelf life, as they can easily be recycled for the next use case. And I think that's also a shame for the people doing the work of developing these things, that they end up being outdated quite quickly. So Matthew says I have 5 minutes left, so I'm just going to breeze through the last bit here and get to the point. And the idea is that we have different use cases that are not tackled holistically, but basically, we work often on the same problems. So if we can solve these use cases holistically, we have more time for physics, we get better and more reliable results, and the contributions of the individual developers have a broader and longer lasting impact in the collaboration. And that's basically what we've tried to do in what's called the GraphNet project that was used for this paper here, where we're trying to develop reusable genome components that are plug and play, and all those components sort of allow you to go from your training data to deployment in physics end to end. All of the code is validated following best practices, and it's applicable across all of IceCube for all different physics use cases, but it also easily extends to other physics experiments, both other optical neutrino telescopes like IceCube, hopefully others as well. So I think I'm actually going to stop here. There's some other material, but I think that the important point I want to make here is that to advocate for trying to approach machine learning in a little bit of a different way, and think about how we can build machine learning systems and platforms rather than individual solutions. Because if we do that, then everyone's better off. In my experience, contributions live on beyond the individual physics analysis, and we get better physics as a result. So we try to do that in our own little way here. And if people are keen to talk more about it or contribute, then you are all the more welcome to have a look here. But I think that's it. Thanks so much for listening, for letting me come here and chat. And I think we maybe have time for a few questions.
Great. Thanks very much, Andreas, for a very interesting talk. And I think you made some important points at the end there that we agree a lot on. So we've got time for a couple of questions. Pritam?
Hi, thanks for the nice talk. Can you go to slide 30 where you were showing the neutrino energy resolution improves up to 100 GeV?
Yeah.
Yeah. So do we understand why after 100 GeV this energy this performance degrades?
Yeah, I think it's a very good point, and I think it's true here and here. It's a general trend. So I think there are two reasons I can think of that would govern this. And one is just pure statistics. So the sample on which this was trained and evaluated is not uniform in energy. So it's dominated by events in this area here from 0.5 to 0.15, which means that the network has just not seen enough events at these very high energies to become really competitive up there. So that'll be one argument. And specifically for the scenes reconstruction here, it probably also has a lot to do with the specific problem that's being tackled. Because for you can't quite see this here, but the dashed lines here are the cascades, and the fill lines are the track-like events. Of course, the track-like, you have an elongated shape. It's easier to sort of estimate the pointing of that event than a cascade that's spherical. But here we see that the GNN yields pretty uniform improvements for the cascade events, but it really tanks at the high energies compared to retro. Well, relatively speaking, it's still good improvement. So in this case, it's also just because at these high energies, the task of doing a line fit essentially through the event becomes comparatively easy, which is what retro is really, really good at, like those line fits that match the model quite well. So the combination of the characteristics of the tasks changing with energy and the statistics, I think, is what really drives this impact here.
Okay, so can it be improved? If there is some specific reconstruction, specific network, for the 100 to 1, 100 to 1 TV, just taking this energy range.
Potentially, I think one way to improve it would just be to be a little bit more sort of. Right now, the papers focus on the low energy range, so it kind of does what it was meant to do. If we wanted to extend it to high energy ranges, we could be smart about how we choose the data set on which this is trained to have uniform distribution. You could have separate sort of networks for both ends of the spectrum, and there's a reason that could work, because at the low energies you have very few pulses. So having 8 pulses interconnected means that you basically encapsulate the whole event, whereas at the high energies you can have 1,000 pulses, which means that the connectivity has a very different characteristic. So you're right, you could either solve that with different networks or being clear about the architecture and your connectivity and so on to make it scalable across the entire energy range. But we haven't really pursued that yet.
Yeah, okay, thanks.
Naharika, do you want to ask your question?
Hi. So I was just worrying about the fact that the nodes in your GNN correspond to data that do not come from are not IID, because one pulse is very, very correlated with another one. So I was just wondering if you have thought about how that affects your inference.
I think it's a pretty interesting question, and I think a good analogy here is CNNs and image data, where the pixels, nearby pixels, they're not IID either. Like, they're highly correlated, but that's exactly the correlations that we are exploiting in these deep neural networks. In the CNN, you learn kernels. You train kernels that learn these local correlations, and some correspond to edges and some corresponds to corners and whatever. And explaining what the model learns is not something we've gotten to quite yet, but the intuition is that you want to learn those local correlations. You want to learn radiation patterns in the event and use that as the basis for saying whether it's a muon or some other particle and so on. But that's as far as we've thought about it, I'm afraid.
Okay. Do we have any more questions for Andreas? Yes, Eric.
Hi, thank you very much for the very interesting talk. So on the various GCNs that we see from IceCube, is any of the localization that's offered or the information about the event coming from any of the algorithms that you provided?
Could you repeat the question again? Sorry.
There is the GCNs, the notices that IceCube sends about the high energy neutrino events.
Yeah.
Any of the information there reported coming from the algorithms that described today?
No, not yet, I would say. So right now, this is only being sort of demonstrated in Monte Carlo before being applied in actual data. But ideally, you know, a direction that we want to pursue is using these for alerts, because you know they are fast enough that they could be used in real time, and you could have some GCN alerts that were based on this. But right now, unfortunately, that's not the case.
This is exactly what was driving my question, namely, at least for some events that time is of the essence, and that's the purpose, of course, of GCN. And if I can continue, Matthew, you can stop me if we're running out of time. Have you attempted the use of machine learning for the core collapse supernova identification? I guess when you're talking about low energy neutrinos, I thought you were going to be talking about core collapse supernova neutrinos. But
yeah, I guess like that's a whole regime, even like MEV that's even lower than this, for which core collapse supernova would be relevant. I'll say that, you know, it's something that's being investigated, but we don't have any public results yet.
Thank you.
Well, that's an intriguing response there, Andreas. Meghna?
Hi, Andrea. Thanks very much for the very nice presentation. So you talked about the comparison between performance of GNN versus dense CNNs. I was wondering if you considered, or IceCube has considered, performance comparison between sparse convolutional networks and semantic segmentation versus how much you gain with GNNs.
I think it's a really interesting question, because you're right. One of the points I make is that, you know, as regular density has to process the entire event, but you're right, that doesn't have to be the case. And we see results from Microboon and Icarus who use sparse CNNs, and it actually works incredibly well. It's not something that's been investigated in IceCube. My intuition is that it would result in a performance gain. But the paper on the dense CNNs came out last year. So that in itself is actually quite cutting edge. And I think then that the vibe in IceCube has then shifted a little bit towards GNNs, because you're right that the sparsity of the event is much better solved by sparse CNNs. But the other sort of conceptual challenges, like the geometry and sort of the nesting of detectors, that's still a problem.
I see, makes sense. Thanks a lot. The other question that I had is more general machine learning applications in IceCube. So I was wondering if you have implemented machine learning algorithms at the trigger level itself, or is it only at the reconstruction level? Or do you think you'll gain by implementing machine learning algorithms at the trigger level?
Excellent question. I'll preface this by saying that I've been at IceCube effectively for 6 months. So there's a big chance that I'm talking out of my ass. I don't think that's been done in IceCube quite yet, because you know, for that to work, it would have to be one of these deep algorithms. And those are still just maturing to the point where we apply them to data. So to my knowledge, not yet. But like, this tells us that it should be feasible to do that. But of course, doing it at the trigger level on device FPGA, again, that's another can of worms.
All right. Yeah. Thanks a lot. I should admit that I'm a Microboon collaborator.
Okay, perfect.
Thanks again.
No worries.
Okay, Eric, did you have another question or?
If we have maybe one more minute, I was wondering if you have tried to use, or I guess I'm asking how transportable this algorithm is, let's say, to Antares, and have you tried to use that, to Antares data, assuming that there or you have access to that?
A really interesting question. I think one of the things that we've pursued in the Neutrino Telescope community over the past half year has been to set up a machine learning working group between IceCube, KM3D-Net, P1, Antares, and so on, to facilitate exchange of tools and knowledge and ideas and so on. And I know that these folks are pursuing similar ideas. We haven't tried. We're sort of working with exploring data from other experiments, and it should be directly portable. And that would be the whole selling point, that if it's on the South Pole or in the Mediterranean or in the Pacific Ocean or some lake in Russia, the structure of the data, the structure of the detection method is exactly the same, and the tools could be exactly the same as well. So we're in the process of applying it to other experiments, and it should be straightforward. But we haven't worked with Antares to do that.
And we have another question from Joshua in the chat window. Joshua, do you want to ask a question?
Sure. It's just how much work went into the deployment and pipeline as opposed to the actual model to do a reconfigurable GNN? And was it using standard tooling, or did it involve a large library of custom code?
So we've done some work on both ends, and right now, we've spent most of the time on sort of just skip a little bit here to here. So we've spent a lot of time on developing sort of the Lego blocks of the GNN to sort of to abstract away the details of how you actually wire the thing and just focus on what's your detector, what's your physics task, and what's your GNN, and then spend some time on the deployment pipeline and so on. But that's still sort of maturing. And in terms of your question about tooling, we're trying as much as possible to build on industry standards like PyTorch, PyTorch Geometric, PyTorch Lightning, Docker, weights and biases, and so on, and have as little custom code as possible. The whole mantra about standing on the shoulders of giants. And then we're only trying to build a simple layer on top of that to hide the details from non-ML experts.
Thank you.
Yes.
Okay, well, if we've got nothing more, I think we're a good 10 minutes over the hour. So thank you again, Andreas. This has been a great talk and some really interesting stuff here. I think they'll make for good follow-up discussions. Okay, everyone, the next A3D3 seminar will be in 4 weeks' time, so it'll be this. I'm blanking now on the date. We'll send out a notification.